So guys, in this example, S is a set containing 0, 1, 2, 3, 4. So S is basically a set of whole numbers and a relation R defined from S to R. So S is a set of whole numbers and R is set of real numbers. Okay. Such that X, R, Y, if and only if ln Y is equal to X, ln 3 by 7, where X belongs to S, that is whole number, and Y is a real number, guys. Okay. Y is rather a positive real number, guys. So we have to find the sum of all elements in the range of R. So how should we proceed with this? What should be the hint to this question, guys? So the hint is, guys, the way it is defined, this equation, if we solve a bit, okay, so, and we try to substitute some values of S, and we try to recognize a pattern in the value of R, because there would be infinite values of in the range, because there are infinite values, whole numbers in this domain that we are substituting. So we will try to find the pattern when we add them, and accordingly we will find the sum. So first we will try to solve this, simplify and solve this in the solution part. So this X will go in the next step in the power of 3 by 7, like this, guys. X will go in the power of 3 by 7 using the property of log. K log m is equal to log m to the power k. So ln both sides are cancelled again from the property. So we will get the equation relation between y and x as y is equal to 3 by 7 to the power x, and x is set of whole numbers. So it starts with 0, 1. For 0, value of y is 1. So 0, 1 is an element of R. Similarly, when x is equal to 1, the value of y is 3 by 7. Similarly, when x equals to 2, similarly it will be 3 by 7 to the power 2. So we can recognize a pattern that 1 plus 3 by 7 to the power 1, 0, power 1, power 2. So this reminds us of what, guys? This reminds us of infinite GP plus AR square up to infinity, where A, if you see, it is 1, which is 3 by 7 to the power 0. Common ratio is 3 by 7. So using A upon 1 minus R, substituting and solving it, we will get the value of the sum of range as equal to what, guys? 7 by 4, which is the answer. So in this question, guys, a set A is given 2, 3, 4, 5 up to 15. So natural numbers 2 to 15 are given. A defined number of relations are defined in A, that is the elements, the ordered pair A, B belonging to R, they belong to A square, guys. Okay, A cross A. So R is equal to A comma B ordered pair such that A is an integral multiple of B. We have to find number of relations in A. So guys, clearly we need to understand the meaning of this A is an integral multiple of B. And when we understand this, that would be the hint. Accordingly, we will proceed, guys. Okay. So the hint part is the same thing. A is an integral multiple of B means if we multiply B by some constant k, we will get A. In other words, A is an integral multiple of B also means that A, when divided by B, we will get an integer k, positive integer, because A and B are natural numbers in this question. So how we can proceed with this, guys? So A is clearly a bigger number. So if a number if in order to find ordered pair AB, we will fix the, what should be the approach. The approach should be fix the bigger number so that we can find its factors. The factors are the divisors, okay, or the multiples. So we will start with the max number because A is divided by B. So we will start with A, and in A we will start with 15 and lesser numbers. Okay, like if we start with 15, if A is 15, what are the possible values of B from 2 to 15? So clearly 15 is one of the factor, 3 is one of the factor, 5 is one of the factor. So by fixing A, okay, we can get the values of B, which are basically the factors of A. Okay, so we will start with A, and we'll start with maximum A, which can be 15, and then we'll start for each value of A, we will find value of B, and we start with 15. So and then we will decrease by 1 till 2. Okay, so after 15, 14, 13 and so on, and we'll keep finding value. It will kind of, a bit of calculation, but if it is done correctly, okay, it won't take much time. So A is given to be this. Now for A is equal to 5, guys, as we have seen, what is the value of B? So B is, we have seen B is can be 15, 3 and 5. So there are 3 elements because 3 ordered pair corresponding to A is equal to 15. So once 15 is done, now we will start with A is equal to 14. So for A is equal to 14, what are the values of B? So if you think, B can be 14 itself, then 7 is a factor, 2 is a factor. So corresponding to 14, 7 and 2, we will have 3 elements. So that way we will find for 14. After that, for A is equal to 13, B is equal to 13. Since A is prime, no other factors other than 13. So only one element, because one ordered pair, which is what? 13 comma 13. So that way we will keep doing for 12, guys, which will give us 12, 2, 3, 6, 4, 5 elements. Then 11 for 1, 10, 3 elements, 3 ordered pair. 9 we will get 3, 8, 3. So 9 we will get 2, 7, 1 only. Then 6, 3, 5, 1 value only. 4, 2 ordered pair. So 1 for 2 is equal to 1 ordered pair. So if we add these 1, 1, 2, 1, 3, 1, all the ordered pair, if we add, okay, we will get the value of sum total as 30 elements. So number of elements is what, guys? It is 30. So in this example, a relation R is defined as R is such that ordered pair AB is such that A plus 7B is 39, where ordered pair AB is belonging to n square, means A and B both belong to set of natural numbers. Now in this, so this relation is valid, that I will explain it. So let's complete this question. Then if summation of n equals to 1 to m 3 plus 2 I to the power n factorial equals to p plus iq, then find 2p plus q minus m. So where m is number of elements in R. Okay, so that's how the question is defined. So let's try to understand this question, which will throw some light on the approach, and we'll see the hint. So guys, as you can see here, A plus 7B is equal to 39, and since A and B are natural numbers, so we have to fix one variable. So we'll substitute one, another variable we will get. That way we can get values of ordered pair AB satisfying this. Okay, and this summation, we know that summation gets distributed in addition. So summation f1 plus f2 is summation of f1 plus summation of f2, and the values n equals to 1 to m we will substitute. So in order to calculate this, it is imperative, we need to find number of elements in R. So number of elements in R we need to solve for this a plus 7b equals to 39. Okay, so that would be our approach. So find a b pairs and find m, and then find this summation, equate it to find the value of p and q, and hence we can get the value of 2p plus q minus m, guys. Okay, so uh, the hint would be, we will fix b, you can fix a also. Okay, any one variable if you fix, so in this case if you fix b, so if you fix b we will get a. So because a depends on b, as you can see from this linear equation. So if you put b is 1, 39 minus 7 into 1, 32, the ordered pair corresponding to b is equal to 1 is 32, 1. Similarly for 2 it would be 25, 3 it would be 18, 4 11. Similarly 5 we will get 4. So as you can see, if you can count, there are 5 values of b, so 5 ordered pairs, so m is clearly 5. Proceeding with this sum, we will replace m by 5 here, and summation we will distributing in sum. So like this, the summation is distributed in plus. Okay, so 3 is added 5 times, so 3 into 5, you will get 15. Now the second summation 2 comes out, and we will substitute values from 1 to 5 in this n factorial, so which is 1 2 3 4 5 factorial. Now we know that I to the power 4k, where k is an integer, is 1. So these last two factorials, 4 factorial and 5 factorial, which is in the power of iota, would be 1 and 1 respectively, because of this fact I to the power 4k. I to the power 3 to the 6 would be I to the power 4 into I square, and I square is minus 1. This is 1 plus 1 is 2. I square is minus 1. Okay, which is this. 2 minus 1 is 1. Okay, minus 1 plus 2 is plus 1. I is as it is, 15 as it is. So we will get 15 plus 2i, as 1 minus 1 cancels out. So comparing it, we will get the value of p as 15, q as 2. So 2p plus q minus m, 2 to 15, 32 minus 5 is 27, is the value of the expression, guys. Let's see what are the types of relations. So first is, guys, that we define is identity relation R1, Ri. Okay, so it is defined from A to A. Any identity relation is defined from A to A, provided A comma A is an element of Ri, where A is an element of A. Okay, so this is an identity Ri or identity relation if for every element in A, that is, let's say small a is an element of capital A, which implies A comma A will always be an element of Ri. For every element is also a keyword. Okay, for every element means if there are 7 elements, then all 7 elements should have A comma A. Okay, no element should be left with, and apart from that, A comma A is an element, and secondly, no other element should be present apart from the type A comma A. apart from the type a comma a, no other element should be present. So why I am using this thing, no other element, that I will explain you. We will see when we will see reflexive relation. Let's take A as any set containing -1, 4, 2. So if I define Ri, reflexive relation, from A to capital A, then what is Ri, guys? So clearly Ri, we will take all the three elements -1, 4 and 2, -1, 4 and 2. That's it. Only these three elements we will take, and then -1, -1, 4, 4, 2, 2. That's it. No other element should be there. This is the meaning of this. If a comma a we have taken, that's it. And every element we have taken. For example, if suppose if I ask you here, if I take only these two elements, and if I ask you, is this Ri? So in that case, we will say, no, this is not Ri, this is not an identity relation, because one element, which is 2, 2 is missing. So all the element, each and every element, for every element in A, as I said, it should be a comma a. Okay. So let's take one more example. If A is given to be 0, 3, 7, I define R1 as between the brackets a comma b such that b is mod a. What is mod a? Where a and b belongs to set A, which is 0, 3, 7. Mod a means every number that we put, it gives positive value. Mod a we mean is -1 mod is 1. 7 mod is 7 only. 7 by 2 mod is 7 by 2 only. That is the meaning of modulus of any number A. So B is obviously a positive number, and A and B, they both belong to what? They both belong to set A, obviously. Okay. So we need to check whether R1 is identity relation or not. Okay, so what we will do, the solution would be, we will substitute the value of A and we will obtain B. So we will substitute the value of 0, 3 and 7 in B. We will get mod of 0, mod of 3, mod of 7, which in return gives 0, 3 and 7. So 0 is mapped with 0, 3 is mapped with 3, 7 is mapped with 3. So we will get 0, 0, 3, 3, 7, 7 as R1, and which is what? Is an identity. So yes, the answer is R1 is Ri, or identity, it is relation. Okay, that is what we call identity relation. Now similar to that, rather more generalized version of identity that we will see now is the second kind, which is what we call reflexive relation. Now what is reflexive relation? I denote it by RR. In other literature, other books, there isn't any fixed symbol which is assigned to reflexive relation. I particularly assign it as capital R, small r. R, small r stands for reflexive. So again, it is mapped, it is between two sets A to A, RR. The condition of RR to be reflexive relation in A to A is such that if for every element A to A belonging to A, there is always a comma a element in RR. This is quite similar to the definition that we have seen in identity, but it should be always, that is also there, plus there may be other elements may be present. That is the key thing, that which makes it a rather generalized version of identity relation. Okay, so for example, if I define a set from 1 to 7 minus 1 to the same set as R3, where I define R3 as this. So the question is R3 a reflexive relation in R? Reflexive relation. So we need to check that if there is 1 here, we need to check 1, 1 should be there, which is there. Yes. Then we will check 2. So 2, 2 is there. Then 7. So 7, 7 should be there, which is there. Then -1 we will check. -1, yes, -1, -1 is there. And as I said, there are other element 2, -1, 7, 2, few more elements are there apart from a comma a. So all a comma a are fully exhausted, all element are taken. Okay, for each element we have seen that it exists 1 comma 1 to till 7 comma 7, it all exists. And as I said, there are extra elements also here. Okay, so extra elements, as I said, there may be other elements may be present. So other elements which are present, I denoted them by this arrow sign. So yes, R3 is reflexive. Is R3 reflexive? So yes, we can say it is an example of reflexive relation. Moving on to the next example, again the same question, is R4 reflexive, where the set A is defined from 1 to -1. Now as you can see here, related to 1, 1 comma 1 exists, 2, 2 comma 2 exists, -1, -1 comma -1 is not there, -1 is missing in this. So it should be exhaustive. Every element of set A, it must have a corresponding element A comma A in the relation which is missing here. 1 comma -1 is missing here. There is some extra element 1 comma -1 here, which doesn't matter much, but the only thing which is missing is 1 comma -1. So R4 is, if the question is R4 reflexive, so clearly we can say that no, it is not reflexive because of -1 comma -1 which is missing. Similarly, let's take another example. So here A is 1, 4, -7. So again A, R, R. So our reflexive relation, one more example let's take. See, 1 related to 1, 1 comma 1 is there, 4, 4 comma 4 is there, -7, -7 is there, and some extra element 1, 4, and 4 -7 is there. So this is an example of reflexive relation, guys. So we can say that what is the difference between identity and reflexive? So we can say that, guys, every identity relation is reflexive, okay, but every reflexive relation is not identity, okay, because as you can see, the previous examples of identity, what we defined here in identity, all the examples of identity elements, okay, like this. So this is not only identity, this is also reflexive as well, because extra elements are missing. Doesn't matter, because extra elements is not conditional, it may or may not be present. The importance is these three must be present, so which makes it reflexive as well and identity as well. So reflexive, every identity is reflexive, but every reflexive is not identity, guys. Okay, continuing with reflexive examples. Okay, let's take this relation R2 in set of integers z to z. It is defined x r y if and only if mod of x minus 5 is less than 3. The question is R2 reflexive? So how we can approach this? What should be the hint of this? So clearly the hint is x equals to a, y equals to a, because they should be, in order to check x comma y, if it is an element, and we need to check a comma a element satisfies or exists or not, we need to put x equals to a, y is equal to a. So that's how we can approach and we can check. So this is the hint. So now let's move on to the solution. So yes, substituting x equals to a and y is equal to a in x and y, a and get cancels out, gives 3, which is less than 3 is always true. So any integer if you take, for all integer, a comma a will always satisfy this, so it will be a part of R2. So it means R2 is what, guys? Yes, R2 is reflexive. Now let's take another example. Let A and B represents triangles. Here A and B are not any numbers or something. They are represent triangles from a plane containing triangles, which is I denote by set of triangle. I denote it by capital A. Capital is a set of triangles rather. Now I define a relation R2 A R2 B is such that it has to be if and only if A and B are similar triangles. A comma B is R2's relation if A and B are similar triangles. Then is R2 reflexive? So again guys, the hint should be, if we will take A and B as same, like A comma R2, and we will think what? We will think the same, like A comma A, if the two triangles are same, if the two triangles are same, are they similar? That we need to think. So if we think, that comprises our solution. So yes, if A comma A, if you take AR to A is similar to A, which is true, although it is congruent also, but it would be similar also, always. So yes, it is reflexive relation, guys. Okay, let's take another example, guys. A R B, if and only if A plus B is a composite number where A and B belongs to set of natural numbers. Is R reflexive? That's the question. So again, the approach should be replacing B by A. That would be the hint. A and A plus A, we need to check, is it a composite? Is it always composite or sometimes composite? That we need to think. That comprises, that's our hint part. So the solution part, proceeding further, adding A and A, replacing B by A, we will get 2A. So 2 is multiplying to some other number, means it is composite, because composite number means what? Composite number means it is multiplication of two numbers, at least two numbers. Prime number is single number only. It is not composite. Prime number we can multiply by 1 only. Okay, but composite number, it can be of the form 2, 3, 17, 9, 4, 8 and so on. So this is composite number, where the constituent numbers, none of them, either of them is not 1. All are different than 1. So it's, yeah, it's a composite always. Yes, so it's, since it's always composite, we can say that R is reflexive relation, guys. Okay, let's see questions from mains 2025. Okay, it goes like this. There is a set given A is -3, -2, -1, 0, 1, 2, 3, and a relation x r y if and only if x is x square plus 2y is greater than equal to 0 and less than equal to 4. Okay, so x r y, the elements of A. Let L be the number of elements in R and small m be minimum number of elements required to be added to R, to the relation, to make it reflexive relation. Then what is L plus M? We have 4 options belonging to mains 25. So let's understand the meaning of this question, guys. So the relation is defined by this inequality, which is in 2 variables. So definitely one we need to fix. We need to fix one variable, so that another variable, if you fix x, we can get y. That would be our approach to get this relation, because we need to find the relation first and all the elements also, because the question is asking for L, which is the number of elements in R. So we need to find the relation by fixing one variable and obtaining the other variable xy, and hence obtaining the ordered pair xy. m be the minimum number of elements. Now after once we are clear with the relation, then we can find out what elements, how many number of elements m that are needed to be added so that the relation becomes reflexive relation, guys. So first step is to find number of elements in R, and followed by m, that is the minimum number that we can find after that. So that would be the hint and strategy to solve this. So we'll fix, as I said, we'll fix one variable x in the inequality and get y inequality, that is the range of y, and from that we can get y, because x, y both are elements of capital A. Now after all x are obtained, we can get all the values of y, and hence r is known. That's how we will approach this problem, guys. So in the solution part, we will fix x as -3 or +3, because the value of x square would be same, that would be 9. So adding -9 both sides, this becomes 2y minus between -9 to -5, and y dividing by 2, it becomes -4.5 to -2.5. So y is equal to -3 is the only value which is satisfying. So if you see, for x equals to -3, y is -3. For x equals to 3, y is -3. So there we have two ordered pairs for this relation, x equals to -3 and 3. It should be noted here that -3 is a 3 is missing. So 3 is missing, so 3 will be added later, that we will see. Okay. Now similarly, when we fix x as -2 and +2, x square becomes +4. Adding -4 both sides, this becomes -4, 2y, 4 cancels out 0. Dividing by 2, it becomes -2 to 0. The value of y from -2 to 0 is -2, -1, 0. So for one value of x, we have 3 values of x, so 3 ordered pairs. So similarly, for another value of x, which is +2, we will another 3 values, 3 ordered pairs. So total 6 ordered pair we got for x equals to -2 and +2. In the similar, proceeding with the same x +1, -1, and when we substitute, x square becomes 1. Subtracting -1 and then dividing by 2, y comes in the range of -half to 3/2, which is satisfied by y is equal to 0 and 1. So as you can see, y is equal to 0 and 1 for x equals to -1 and 1. So when x equals to -1, we have y0 and y1, so 2 ordered pair. Similarly, when x equals to 1, we have another 2 ordered pair. So total 4 ordered pair we will have this time for x1 -1. Now finally, substituting x equals to 0 here, x square becomes 0. So directly 2y is between 0 to 4. So y between 0 to 2. So y is 0, 1, 2. So corresponding to x equals to 0, y is equal to 0, x equals to 0, y is equal to 1. So 3 ordered pair. So all the ordered pairs that we obtained from the cases that we took, we got 2 first, and then 6, then 4, then 3. Adding all this, we will get L, which is the number of ordered pairs in the relation. Now if you see, -1, -1, 2, 2, 3, 3 is missing. Okay. From those cases, I referred to the missing of 3, 3 in the beginning of the solution part. So here also -1, -1 is missing 2. 2, 2 is also missing. 3 are missing. So m, number of these many ordered pairs, if they are included in in R, then it becomes reflexive, because for reflexive, a, should be there, all possible a. So L plus m, which is 18, is the answer, and which gives which option? Option number D. Okay. is the answer. The next type is what we call symmetric relation. Okay, how do we define a symmetric relation, guys? So a relation I call R small s. Small s stands for symmetric on set A. So yes, it is defined from set A to set A, Rs. This is said to be symmetric if and only if AB is an element of Rs, then BA should also be element of Rs. For all AB which are a part of, which are an element of set A. Okay. Also, if you look at it closely, AB, BA all are there. It means if you try to find its inverse, then it is same. Rs is equal to R inverse S. So in case of symmetric function, its inverse function is same. Let's take an example with respect to set A 2, 3, 11. R1 relation is defined as 2 to 3, 11, 11, 3. This is an example of a symmetric function, because as you can see, if 3 comma 11 is a part of this, 11 comma 3 also is present in 3 comma 11 is there, then 11 comma 3 is also present in the same relation. Okay, 2 comma 2, since it is equal, we won't take, it is 2 comma 2 belongs to 2 comma 2 only, so this doesn't matter if both are equal in symmetric. Okay, so this is so we can say it is symmetric. Or you try to find the inverse of this R1, which if you try to reverse them, okay, interchange AB, you will see it will be same. So that way also we can check or we can prove that it is symmetric. So this is an example of a symmetric function. Now the question arises how to find if a given relation is symmetric or not. So guys, what we need to do is, first we need to identify the distinct pairs like AB and CD. Try to write them or try to identify them. Okay, distinct ordered pairs, because if they are same, A comma A belongs to A comma A, applies A comma A, that won't be a problem. Okay, that also we will see. So A comma B, C comma D. So we need to check the presence. Once you identified them, you need to check for the presence of their this thing B comma A interchange ordered pair. So if you have identified AB and CD, you need to identify BA and DC. If you identify it, if they exist, then you can declare, you can conclude that it is a symmetric function, guys. Or as I said, this would be a bit lengthy, but still it holds. You find the inverse and check whether it is equal to R or not. Okay, that is also good. And as I said, if all the elements are of the form A comma A type, so it would be symmetric only. Or in other words, if elements of the type B comma A comma B, they does not exist, only the element of the type A comma A exists, then also we can directly declare that it is symmetric function. Let's take this example now. A is given to be 1 minus 2 minus 8 and R1 is defined as minus 2 minus 8 minus 2 1. Minus 2 minus 2 minus 8 comma 2 is R1 symmetric. So again, as I said, if you can identify numbers A and B which are unequal, so if minus 2 minus 8 if you identify, then minus 8 minus 2 you need to search for, which you got, so this is okay. Now in the similar way, minus 2 minus 1 minus 2 comma 1 if you identified, you need to search for 1 comma minus 2, which is not there. minus 2 is there, which is of no issue here. Okay, it has nothing, we won't take into consideration, as I said. So 1 comma minus 2 is not there, so we can say that this is, as I said, 1 minus 2 comma 1, that is not there, so we won't say it is symmetric. We said it is not symmetric, guys. Now let's take one example. Now, as I said, if set A 7864 in a relation only equal elements A and B are given. Okay, so the first question, is it reflexive? So in order to check whether it is reflexive or not, we need to ensure that all elements of A related to that, we need to have an ordered pair of form A comma A. Now as you can see, 6 comma C is not there. With respect to 8 comma 8 is not there. Okay, so reflexive it is not. Okay, so it is not a reflexive relation, guys, that we can say. What about symmetric, guys? So in order to check for symmetric, there is no such number ordered pair of the form AB or BA. So if there are only equal numbers like this or this, directly we can say that it is symmetric. So reflexive it was not, but symmetric, yes, we can say it is symmetric. Okay. Let's take one more example of similar sort. A is 7864. Now as you can see, it is 77446688. Is it identity? Is it symmetric? So we know identity from the relations are those relations in which A comma A ordered pair exists, and every related to every element of A it should exist. Related to 7 comma 7 should exist. Related to 8 comma 8 should exist. Every 6 4 also, as you can see, it exists. Nothing is left. All exhaustive or ordered pair A comma A are there. So yes, we can say that it is an identity function. Now as I said, if all the ordered pairs are of equal numbers, A and B are equal, symmetric, directly you can say it is a symmetric function. It's symmetric relation. Okay, guys, because there are no such numbers A comma B for which we need to hunt for B comma A. So directly we can say it is symmetric. So it leads us to a question that what is the relation between identity and symmetric relations? Is there a relation? So if you think a bit, you will come up with this conclusion that yes, every identity is symmetric, but if you think about every symmetric function, definitely it won't be an identity relation. Okay, that's the relation between identity relation and symmetric relation. Let's take few examples on symmetric functions. For example, if there is a relation A-RB which is such that A plus B is composite number where A and B are natural, the question is this relation symmetric? So A plus B composite number, we know that it is of the form 2 into 3, 7 into 9, 11 into 3 into 5. Composite numbers are not prime, like 2, 5, 7, they are prime numbers, they are not composite because they don't have any other factor apart from themselves and 1. So the solution is, we can start with, if we assume that A plus B is composite, then if we can arrange A plus B as B plus A, so definitely it will also be composite. So A comma B leads to B comma A, definitely always. So we can say that this relation is symmetric. So let's take another example, relation R2 in set of integers defined by x r y, if and only if mod of x minus y is less than 3, is R2 symmetric? So x comma y in the previous example also, we will interchange a comma b. So here also we will interchange x and y. So let's, if x comma y means mod x minus y less than 3, y comma x means mod of y minus x less than 3. Now taking minus 1 common, taking out minus 1 is 1, this becomes x comma y only. So it means x comma y leads to y comma x leads to x comma y always. So it is, we can say, a symmetric relation. Similar to this, now let's take another example. Let a and b represents triangles. Now here a and b are not any numbers which they used to. Now they represent distinct or same triangles from a set of triangles capital A. A relation R2 between A and B triangles is such that it implies if and only if a relation exists if A and B are similar triangles. Then is R2, this relation, a symmetric relation? So again we will assume A and B as to be similar. Like if A and B means A is similar to B, if it exists, so if A is similar, B is also similar to A. That is a natural fact we know from similar triangles. So A comma B logically obviously leads us to B comma A, which means it is a symmetric relation. Okay, moving on to the another example now, which is asking A is 0, 805 minus 7, R1 is 880055 minus 7 minus 7 0, 5. We have to check if R1 is reflexive and symmetric also. So for reflexive with respect to 8, we need to check for 8 comma 8 which is there, 0, 0, 0 is there, 5, 5, 5 is there, minus 7, minus 7, minus 7 is there. So 0 comma 5, 0 comma 5 is, it doesn't matter for reflexive. So reflexive it is there because these four ordered pairs which are equal, A is equal to B exist. All the elements of A related to B have a ordered pair A comma A, so it is reflexive. What about symmetric? So as you can see, 0 comma 5 is distinct. 0 comma 5 we need to search for 5 comma 0. Is 5 comma 0 present in R1? As you can see, 5 comma 0 is not present, so this is not symmetric, although this is a reflexive relation, guys. So guys, in this question, let A is 3, 4, 5, 6 up to 98. So A is a set containing 98 till 98 natural numbers starting from 3, and let a relation R on A defined as x ry if and only if 5x equals to 2y, means where x ordered pair belongs to A square. So x and y both belongs to the set A, and they also satisfies this relation 5x equals to 2y. Okay, to define this relation, the question is we have to find minimum value of m elements that can be added, that are to be added to R to make it a symmetric relation. Now what is the meaning of this last three sentences? Minimum value of m, like whatever R that we obtain by suitably choosing x and y, okay, which satisfies this equation 5x equals to 2y. So once we get R, the relation satisfying 5x equals to 2y, where x and y are elements belonging to the natural number set 3 to 98, there are so many elements. Like if, for example, if we get, if one of the element in R is, let's say 2 comma 5, okay, as you can see it is satisfying this. So if 5 comma 2 is not there, this is an element of R, okay. If 2 comma 5 is there but 5 comma 2 is not there, then 5 comma 2 we need to add, okay, then only it would be symmetric. So we have to check all those ordered pairs whose interchangeable ordered pairs. Like if AB exists and BA does not exist, then BA we need to add. So minimum we have to add. So that many we have to add. We can add additional also, still it would be symmetric. So that's why the keyword minimum is used here. Okay. So that's how we will, that's the meaning of this question, guys. So how we will approach this, guys? So clearly 5x and 2y are equal. So we will try to find ordered pair xy. So what we will do, we will write it like this. We will take 2 left hand side and 5 on the right hand side. And this equation x by 2 equals to y by 5, will assume it to be k. So x by 2 is equal to k means x is equal to 2k, y is equal to 5k we will get. So now instead of xy, we got an ordered pair in terms of k only, where k is a natural number, k has to be a natural number. So we will assign the value of k as starting with 1. So 2 comma 5, definitely it belongs to this set 3 4 5. So it does not belong to this set 3 4 5, because 5 belongs but 2 does not belong to it. So k will starting with k is equal to 2. So 4 to 10, 3 4 5 up to 98. 4 belongs to this and 10 also belongs to this. So 4 comma 10 is an ordered pair which is acceptable for k is equal to 2. K is equal to 1, it is not acceptable, okay, because 2 is not in the set of A. So as you can see, this value of the second value B is greater than the first value. It always will be, because 2k 5k it is. So we can find the value of k max, okay. How? So it is 98. So 5k which is increasing faster than 2k, it will reach 98 earlier than 2k. So we will impose a constraint on 5k, which is, it has to be less than equal to 98. So from this we will get the value of k max as 19.6. So k is equal to 19. So it means R has how many ordered pairs? So R has ordered pair starting from k 2 3 till 19. It will have 18 ordered pairs instead of 19, because k is equal to 1. We saw it was 2 comma 5 and 2 was not included in A. So R has 18 ordered pair. So all are of the form p comma q, because as you can see 2k is not equal to 5k. So they are all of the form p comma q, where p is not equal to q. So to make it symmetric, we need to add what, guys? To make it symmetric, we need to add element of the form q comma p for every p comma q that we have in R. So number of p comma q, initially I miscalculated, so it is 18 now correctly. So now number of q comma q that needs to be added is 18. So this is the minimum value m, guys, okay, and that is the answer to this.